In this presentation with the title Manipulating GUI Structures Declaratively, we will present a domain-specific language for developers to program structural changes in GUIs. My name is Knut Stokke, and together with me on this project are Mikhail, Barash, and Jaakko Järvi. So let's first notice that GUIs have all kinds of structures. When we look at the components of GUIs, we see that they are organized into trees and grids and lists and so on. This talk is about how programmers can manipulate these structures. As a few examples of such structural changes, we can see, for instance, in the Google Maps GUI, where the user can change the route by dragging and dropping the intermediate stops, which has impact on the rest of the GUI. On the Alarm app on smartphones, the list of the alarms might be reordered whenever the user updates one of the alarm times. In this case, the user aren't directly manipulating the list as with the Google Maps example. It's rather a consequence of a state change. Another example is this website for booking multi-city flights. This particular user interface is designed so that if the user updates the to field of one flight leg, the from field of the next flight leg is updated too. There is also a constraint on the departure date. The user is not allowed to choose a date earlier than the departure date of the previous row. We can assume that there exists some connection between these rows, and if the user would want to insert or remove a flight leg in between two other flights, these connections would have to update as well. Here, and in many similar applications we have encountered, inserting and removing in between rows are not provided to the user, even though the scenario of performing these operations is quite likely. Anytime there is a list or a tree structure in a GUI that users can edit, we expect the user to be able to manipulate the structure. In all these examples, there is a view and probably some underlying model, which may contain all sorts of constraints and dependencies. And the view and model need to stay in sync, and making sure these things change correctly is the reason why programming structural changes in GUIs is rather complex. The point of our work is to try to make programming structural changes as simple as possible. Really as simple as working with any well-specified data structure, such as lists, queues, trees, and graphs. We have created a domain-specific language, or DSL, for programmers to manipulate structures dynamically. To explain how we can specify structural changes in our DSL, we will look at one particular case. This application is from Apply, Texas, and hundreds of thousands of students use this every year. In this form, the students input their extracurricular activities, where each activity in the form contains 23 input fields. The student can give anywhere from 1 to 10 activities, and the form instructs the students to give the activities in the order of relevance. But for some reason or another, the Apply Texas developers have not provided any operations to reorder the activities, which really hurts the user. We think this is a general phenomenon, and argue that structural changes are often too much of a pain to program correctly, so the developers would not provide the features that would be convenient for the users. So what are the operations the developer could offer to the user in this case? The user should be able to insert activities into the list, remove activities from the list, and swap to subsequent activities. Like I said earlier, the goal is to make it easier for programmers to manipulate structure. The structure can be in a messy form in a GUI, so we developed this DSL where we aim to tease out the structure and make it explicit, and then allow the programmer to specify changes in a clear manner. Let's look concretely at what our DSL looks like. So we have a transformation rule swap that takes two components A and B as arguments. Before the transformation, we expect that A precedes B. And by precedes, we mean that B directly follows A. And after the transformation, we want that B precedes A. The transformation rule remove takes three components A, B, and C. And here we expect that B is between A and C before the transformation, and it's not after the transformation. And the transformation rule insert is just the opposite of remove. So what is precedes and how is it defined in our DSL? Precedes is a relation defined on two components A and B. Between the triple quotes, we have code in the actual GUI programming language, which in our case is JavaScript, but this could be any language that the programmer used to develop GUIs. We use string interpolation to insert placeholders in the JavaScript code, in between these gilmet quotes. The relation has three JavaScript procedures. Test is a predicate to check whether the relation holds on the two component arguments A and B. As we will see later, A and B are here defined to be an object with two properties, view and model. We specify that A precedes B if B directly follows A in both the view and the model. The next two JavaScript procedures, establish and unestablish, is executed in order to make the relation hold or not hold, respectively. To establish the relation precedes on two components A and B, we insert B after A in the view and in the model. To unestablish the relation, we choose to remove B from the DOM and the model. Let's now look at these A's and B's and C's. As we've seen, these are arguments in the relations and transformation rules, but they have a predefined component type. We call these arguments placeholders. In the placeholder section, we define A, B, and C to be a placeholder of the component activity, which is a component that we define in the DSL code. So when defining components, we give it a name and an accompanying JavaScript predicate to check if some JavaScript object or value is a component. In this case, the predicate tests that the object has two properties, view and model, which are of some specific types. Notice that in the DSL code, a component can be just about any JavaScript object. In our case, it happens to be something that has a view and a model. To the left, we see how the DSL code looks with everything combined. From the DSL code, we generate JavaScript code with a function for each transformation rule. Let's zoom in on the transformation rule insert and the insert function generated to the right. When this function is called with some component arguments, the function unestablishes all the relations on the left side of the arrow and establishes all of the relations on the right side. The function also performs some additional checks, just to report to the programmer if there is a bug. Let's now look at what the relations and rules are formally. Here, capital R denotes all relations and capital C denotes all components. A relation R on components C1 through CK is a tuple consisting of the components C1 through CK, a predicate to test whether R holds on the components, a procedure to establish R, and a procedure to unestablish R. A transformation rule T is a tuple with components C1 through CK. A sequence of relations on these components, we call these premises, and another sequence of relations on the components, which we call consequences. So applying T unestablishes the promises and establishes the consequences. And note that these are executed in the order that they appear in the sequence. And also note that the establish and unestablished procedure are arbitrary post-language code and can have side effects and so on. And therefore the order of the relations may matter. So the rules might look more declarative than they really are. We will now show you an example where we, with our DSL, has implemented structural changes in a timetable planning application. The events in this application has a start time, a duration, and an end time. And the events are connected so that the end time of one event is equal to the start time of the next. There is also a connection between a day and its first event and last event. We use another library which uses a constraint system to maintain these dependencies between the variables. So if I update the duration of event 1 to 1 hour and 50 minutes, then the start and end time of the next event change, as well as the end time of the day. In this application, there are a lot of dependencies we need to maintain when we break things apart. To perform structural changes, we'll not only have to reorder the HTML DOM nodes, but also update the dependencies in the underlying model. And when we change the structure, we also need to differ between several cases. For instance, inserting at the beginning of a day is not the same as inserting in between two events or at the end. So in an old school in-house application, we would typically have a GUI that allows us to add events at the end and nothing else. But thanks to our DSL, we can now model all the structural changes we want for the application. We are now in Eclipse, and we have used the language workbench Eclipse Xtext to implement tool support for our DSL. So we specify the components in our DSL here. The components are event, day, and calendar. And we define the relation precedes on two events. In the established procedure of precedes, we both update the HTML DOM and the connections between the two events. We also define the relations between events and days, and between days and the entire calendar. Next, we specify the transformation rules. So in order to cover all the cases, we actually need quite a few transformation rules. But here we think each rule clearly communicates its intention, which is the structural change it represents. So when we save the file, the IDE generates the JavaScript code for us with the transformation functions, which we can then import into our application. We can now add some buttons to our GUI, and the event handlers to these buttons that trigger structural changes are now trivial. It's just calling one function generated from our rules. So now the user can swap components and add components at the beginning and in between events and at the end, and the connections are correctly updated. At the end of this presentation, I'll mention some of our ideas for future work. We have noticed that the same structural operations repeat for several applications. So really it's just the relations that need to change. And insert and remove and swap and all these rules remain. We therefore want to see if we can introduce generic rules in our DSL, so rules parameterized over relations. Here we give an example of what a generic version of swap would look like. We also want to explore annotating relations with algebraic properties in order for tools to reason more about the code. Thank you.